Okay, in this video presentation, I'm going to discuss simple and multiple regression, and more specifically, how to run and interpret the results of these analyses using SPSS. So, as a starting point, I want to show you a few models based on this data right here. Essentially, I've got in SPSS, I've got a data file with a measure of student achievement, a measure of mastery goals, student interest, and student anxiety. So essentially, these are the variables that we're going to be working with. So the column header is essentially reflecting the variable that we're working with, and then each row is reflecting an individual student's responses to those measures. I have performance goals in this data set, but I'm not going to use it as a predictor in the model. So at any rate, what is the difference between simple and multiple regression? Well, basically, simple regression entails the use of a single independent variable as a predictor of a single dependent variable. So this is my IV, this is my DV. So and I've drawn these figures out in the Amos structural equation modeling program because it's got a really nice graphical interface, and so it's really useful in drawing things out. So we're not running our analyses through Amos, but I'm using this just as a vehicle for conveying the models that we're going to be looking at. So in this, so the boxes are representing a measured variable or manifest variable, and that's the variable that we have data on in our data set. The single-headed arrow is reflecting the predictive relationship that we're studying. So you can see right here I've got three separate simple regression models that are laid out. The first model has mastery goals as serving as a predictor of achievement, anxiety serving as a predictor of achievement, and then another model where interest is serving as a predictor of achievement. So these are three simple regressions. Basically, with simple or multiple regression using least squares estimation, the dependent variable is treated or assumed to be continuous, and the independent variable or variables, if we're in the context of multiple regression, they are assumed to be, they're oftentimes measured as continuous. It is possible to have a factor as a predictor, but generally that entails recoding the factor into dummy-coded variables. So, and what I mean by factor is just that it's a categorical variable. So we can utilize a categorical variable in regression with appropriate dummy coding. So that's all that means. So for this particular demonstration, I'm just going to make the assumption that mastery goals, anxiety, and interest in each of these separate simple regressions, that they are assumed to be continuous. So with a simple regression, we have a single independent variable predicting variation in a single dependent variable. So for this first one, as I said, mastery is serving as a predictor of achievement. So that's one model. Another simple regression model might be anxiety serving as a predictor of achieve, and then yet another model might be interest serving as a predictor of achieve. So those are three separate simple regressions that could be carried out to study the relationship between one of these variables, one of these independent variables, and the dependent variable. Now we can juxtapose that against a multiple regression, and in this case we still have a single dependent variable. We're still making the assumption that the variable is continuous, but we are entering all of our predictor variables or all of our independent variables into the model at the same time. And really, there are various payoffs to that. One of them is that when we do this, when we start studying the relationship between each of our independent variables and the dependent variable, we're adjusting the regression coefficients for the fact that the independent variables themselves are all intercorrelated. So you can see over here we've got double-headed arrows among all of these variables, and that's signifying that these variables are likely to be correlated at some extent. And so one of the downsides of running a set of simple regressions instead of a multiple regression is that the regression coefficients that would be computed in each of these cases are likely to be biased because of the fact that the independent variables are likely to exhibit at least some level of a non-zero correlation. And so when we are trying to account for variation in the dependent variable, we end up going after redundant information. So that's one of the reasons why multiple regression, if we have a set of predictor variables, why we might choose to use multiple regression instead of simple regression. So that's one of the reasons. Another reason why is because if we look at, I'll draw out a circle here reflecting the total variation in the dependent variable. And so, basically, if I was to look at the relationship between a single independent variable and a dependent variable, then we're only going to explain a certain percentage of the variation in the dependent variable. And if we run a multiple regression, then we can take into account all of the variation or the total variation while also considering the intercorrelations among the variables. So we can explain a larger piece of the pie as a result of the variation among the set of those variables. Keep in mind that our little slice of the pie right here is representing the regression or variation due to the regression, and then the remainder is prediction error. So I'm just going to designate that with a little e, just saying that is prediction error. That's variance that's unaccounted for by the predictors. So if we run our model and we incorporate all the information among our set of predictors, then we explain a larger piece of the pie. So and then one other possible reason why we might select multiple regression as opposed to simple regressions is because of the issue of type 1 error accumulation across a set of tests. So type 1 error just refers to, or type 1 error probability refers to the likelihood of incorrectly rejecting a true null hypothesis. And so typically we set our type 1 error rate or error for a given test at 0.05. That's sort of the conventional alpha level for a given test. And what happens is that when we carry out multiple tests, then the error rate across the set of those tests increases, so that the likelihood of committing a type 1 error across a set of tests is greater than the likelihood associated with a given test. So in other words, if what that basically translates into, let's say that the error rate across a set of tests is 0.15. This would be referred to as a sort of a family-wise error rate. So in other words, if the family-wise error rate, let's say I carry out 3 separate tests right here, testing each of the individual regression coefficients. So let's say the family-wise error rate was 0.15. Then what that would mean is that there is a roughly 15% likelihood of at least one false rejection of the null hypothesis in the set of those tests. So if we carry out a multiple regression, we actually do we actually perform an omnibus test, meaning that we test the combined influence of the predictors in the model as a set. And so by virtue of that, we have essentially one overarching test that tests the joint contributions. And if that overarching test indicates non-significance, then that would, at that point we would not be testing the individual regression coefficients. If it was statistically significant, then we would follow up by testing the individual regression coefficients. But then the type 1 error accumulation would still come into play. So at any rate, let's run through some analyses demonstrating these different procedures. So I'm going to go into the program. I'm going to start off by looking at the correlations among our predictor variables, or independent variables. So I'm going to go through, well, just reiterating this, I'm going to go through correlate bivariate, and I'm going to move our independent variables over, as well as the achieve variable. We can look at that relationship as well, and run the correlations. And so this is basically our correlation matrix for our variables. And you can see in this first column here, we've got our dependent variable, and then we've got our independent variables that are going to be included in our models. So you can see that achieve is correlated positively and significantly with mastery, with interest, and then it's also negatively correlated with anxiety, which is kind of what you would expect. Being higher in anxiety ought to be associated with lower levels of achievement. Then we have, in this part of our matrix right here, these are essentially the correlations among our independent variables. So you can see that mastery is correlated with interest right here. So if I just go down here and go over here, that is mastery correlated with interest at 0.529. We see that mastery is correlated with anxiety at negative 0.262. There's anxiety and mastery. Both of those, just assuming a two-tailed test, are statistically significant. Then we have interest and anxiety, and so there's a negative correlation there as well. So you can see that our independent variables are exhibiting non-zero correlations amongst themselves. So it really does make more sense to run a multiple regression as opposed to simple regressions. But nevertheless, I'm going to run each of the simple regressions and then juxtapose that against the multiple regression. So the first analysis, we're going to go to Analyze Regression and go to Linear. And I'm going to put Achieve in my dependent box, and I'm going to put Mastery in the independence box. If I click on Statistics, I can ask for various pieces of information, including confidence intervals and descriptives. So I'll click on those and continue. And so now you can see we have our descriptive statistics. There's the correlation between the two variables. You can see as we scroll down the model summary table, we have the R-square value, which is referred to as the coefficient of determination. And essentially, R-square is reflecting the proportion of variation accounted for in mastery in Achieve as a function of the predictor being mastery. And R-square is going to range between 0 and 1. So an R-square value equal to 0 would indicate that mastery is accounting for 0% of the variation in Achieve. And a value of 1 would indicate that it's accounting for 100% of the variation. And then a value that falls in between would be that percentage. So in other words, let's say I had an R, well, in this case, we've got R squared that's equal to 0.255. So mastery is accounting for approximately 26% of the variation in Achieve. If you just multiply this number by 100%, that gets you a percentage. And then we have right here an F-test, which is testing the statistical significance of R square in the population. So the null hypothesis is, and I'm going to use the Greek notation, I'm going to use rho and designate with a subscript of y dot x for our predictor variable. Rho is equal to 0. It's actually rho squared is equal to 0. So our R square value is being used as an estimate of rho square. So the null hypothesis is that rho square is equal to 0 in the population. The alternative hypothesis is going to be that rho squared, and I'll just designate it as y dot x right here, is greater than 0. And so the F-test right here is testing the statistical significance of the R-square value. If it's statistically significant, and here we would say it's significant at the conventional 0.05 level, so we would infer that the population R-square, which is rho square, is greater than 0. You can also see right here, this R is referred to as a multiple correlation, and it's just the correlation between the set of your predictors and your dependent measure. It's also going to range between 0 and 1, and it's going to be interpreted in the same way that you would with a standard Pearson's correlation, except that the values will always be positive. So in kind of judging the effect, you would just kind of use, it's essentially kind of conveying the magnitude of the relationship in a correlational index. So really right now these are a little bit less pertinent because we're working with a simple regression, and they become more relevant when we start looking at multiple regression. Okay, so down here we can see that we have our coefficients table. So we have the constant. This is the intercept for our regression line. And so basically, and then down here we have the slope for the predictor. So what we have essentially is, if we think about our data, you can see that basically this is our x variable, this is our independent variable, our y variable, and we would, the data probably looks, something along this line. and we're essentially fitting a regression line to the data. So it's a straight line that's being fit to the data, and the regression line essentially has an intercept, which is the predicted value on y when x is 0, and a slope, which is reflecting the predicted change on y for every 1 unit increase on x. So the intercept for the model is 2.242, and the slope is 0.373. And so most of the time when we're looking at regression coefficients, we mainly key in on the regression slope for the predictor, and we are, in this case, we can see that mastery has a positive predictive relationship with achievement. Now we also have to test this for statistical significance too. So over here we have the significance test. The t-value is just computed by taking the standard error of the regression coefficient and dividing it by the standard error. So t is equal to the regression coefficient dividing it by the standard error for the regression coefficient. So I'll just use the little standard error of b right there. So it's going to equal 0.373. And we're just going to divide that by 0.054, and that's where our t-value comes into play. So that's the 6.877. And so the p-value that is printed out right here, basically we would conclude that if we use a standard p-value or conventional alpha level of 0.05, we would deem that this regression coefficient is significant, meaning that we're going to infer that the population regression coefficient for mastery is not equal to 0. A couple of things to kind of keep in mind. In SPSS, it oftentimes will round off at 0.000. That doesn't mean that the p-value that is printed out here is equal to 0. Generally, what folks will do is they will report this as p less than 0.001. So the p-value is not ever 0. It's just that it's just rounded off, and so keep that in mind when you are interpreting it. Also, in terms of interpreting the regression coefficient, I can say that for every 1 raw score unit increase on mastery, there's a predicted increase of 0.373 units on the achieve variable. So that's how you make sense out of what the regression coefficient is saying. The standardized regression coefficient is also referred to as a beta coefficient, and it's essentially it can be interpreted the following way. We can say that for every 1 z-score unit or every 1 standard score unit increase on mastery, there's a predicted 0.505 z-score or standard score unit increase on achieve. So that's all that is. The other thing to kind of note when we're testing hypotheses concerning the unstandardized regression coefficient, technically speaking, we have the null hypothesis in all cases will be, and I'm going to use a designation of beta here, and basically our regression coefficient is from our sample, which is the 0.373, is serving as an estimate of the population regression coefficient. And the null hypothesis is that the population regression coefficient is equal to 0. And in terms of the alternative hypotheses, there are several possibilities. One, as we kind of did before, is that the population regression coefficient is not equal to 0. So this reflects what is called a non-directional hypothesis. And essentially, if we sort of draw this out using a t-distribution, at the center of the t-distribution lies the null. So the null hypothesis is that, again, the population regression coefficient is equal to 0. And what we're trying to do is determine if our sample estimate departs far enough from the null to reject it and conclude that the population regression coefficient is not equal to 0. So again, this is a non-directional hypothesis. So this is non-directional hypothesis. And when we are testing out a non-directional hypothesis using the t-distribution here, we are essentially putting our alpha level, our type 1 probability, into both tails of this distribution. So we set alpha at 0.05. What that means is that we're laying out 2.5% of the sampling distribution of t in the upper tail and 2.5%, let's write this out, 2.5% in the lower tail of the sampling distribution. And these areas are the region of rejection. So if our sample estimate puts us out into the upper tail or the lower tail, we would reject the null hypothesis and conclude that the alternative hypothesis, we should basically infer that the alternative hypothesis is the case. So in other words, we reject the null hypothesis. Okay, so another possibility, and so basically this p-value right here that is printed out in SPSS is for a two-tailed test. Now, we could also test a directional hypothesis, and so the directional hypothesis, there are two possibilities for a directional hypothesis. One is that the population regression coefficient is significantly greater than 0, in which case, so that would be a directional hypothesis. So I'll just put a directional hypothesis here, and that would imply a one-tailed test. So with this particular hypothesis, we would have our sampling distribution, we have the null hypothesis here, which is the population regression coefficient is equal to 0, but we would put our region of rejection, we would throw all of our type 1 error probability into the upper tail. So essentially when we set alpha at 0.05, testing a directional hypothesis, we're essentially putting 5% of the sampling distribution of t, we're sort of sectioning this off as our region of rejection. So if our regression coefficient puts us up here in the upper tail of this distribution, then we would reject the null hypothesis. But if the regression coefficient that we had, let's say our regression coefficient was something like 0.03 and we had a t-value that would put us kind of in this area right here, then we would maintain the null hypothesis. Or let's say that we had a regression coefficient that was negative, like negative 0.6 or something like that. It would put us over in this region. So this whole area right here, we would maintain the null hypothesis. It's only when our sample estimate puts us out in the region of rejection that we can reject the null. So in this case, we would say that mastery is a significant positive predictor of achievement. Now, there is another possible directional hypothesis, which is that we could say that the regression coefficient, the population regression coefficient is less than 0. And in this case, if we were using our t-distribution, we'd be testing in the lower tail and against the null hypothesis. So if our sample estimate puts us out in the region of rejection down here, then we would reject the null hypothesis. If our sample estimate puts us in this area, then we would maintain the null. So it's really important to keep in mind the hypothesis that you lay out concerning the regression coefficient. If it's a non-directional hypothesis, you can interpret you can just interpret the regression coefficient with that directionality in mind, and the p-value that's printed out right here, it's essentially for a two-tailed test. If you're testing a directional hypothesis, it's very important that the regression coefficient is in the hypothesized direction. If the sign of that regression coefficient is opposite of what you had hypothesized, then you have to maintain the null, even if the little p-value that's printed out right here suggests otherwise. So keep that in mind. Another thing too is that technically, if you're carrying out a test of a directional hypothesis, then the p-value for that test is technically half of what is printed out in SPSS, because this is the p-value for a two-tailed test. So at any rate, we've seen mastery. Mastery has a positive and significant predictive relationship. We'll look at now carrying out a separate simple regression with interest as a predictor in the model. And in this case right here, you can see that looking at our R-squared value, interest is accounting for about 28.5% of the variation. That would be statistically significant using our F-test. By the way, the F-test is essentially uses the F distribution, which tends to be positively skewed, and we're essentially testing in the upper tail of that distribution. So if I set alpha at 0.05, we're essentially testing the 5% region in this upper tail. So 95% of the sampling distribution of F would fall at or below that point. So if the computed F value for our analysis puts us down in this region, we are maintaining the null. If concerning our R-square value, if it's falling out in the upper tail, then we are rejecting the null. So moving down, we can see that we've got our regression coefficient for interest. You can see it is also positive, and we would say that, or interpret this to mean that for every 1 unit increase on interest, there's a predicted increase of 0.384 units on achieve variable. And so you can see that it would be statistically significant. Right now I'm not laying out a directional hypothesis, so we'll just stick with the non-directional, even though logically we could theoretically lay out a directional hypothesis for each of these. And so we would say that the regression coefficient is statistically significantly different from 0. When we look at the standardized regression coefficient, the beta coefficient, we can see it's 0.534, meaning that for every 1 z-score unit increase on interest, there's a predicted 0.534 z-score unit increase on achieve. We'll also look now at the anxiety variable. So I'm going to move this out, put anxiety in, and click on OK. And so now you can see that the R-square value is 0.057, so anxiety is accounting for about 5.7% of the variation in achieve. It would still be deemed as statistically significant in the model. When we look at the regression coefficient, you can see it's negative. So what that would tell us then is that for every 1 raw score unit increase on anxiety, there's a predicted decrease of 0.183 raw score units on achieve. And that regression coefficient is statistically significant. When we look at the standardized regression coefficient, we would say that for every 1 z-score unit increase on anxiety, there's a predicted decrease of 0.238 z-score units on achieve. So those are basically the models that we're talking about. And as I said before, we've already said that our predictor variables, our independent variables, are those variables are actually all correlated. So really running separate simple regressions is quite problematic. Because those variables are all intercorrelated. That would mean that they're in part going after some of the same variation in the dependent variable. Let me just also show you really quickly a graph of the relationship so you can see the regression lines a little bit more clearly for each of these simple regressions. And then we'll run the multiple regressions. So I'm going to go to Graphs, Legacy Dialogues, go down to Scatter Dot here. I'm going to click on this. Click on define, and we'll put achieve as on the y-axis. We'll put mastery on the x-axis and click on OK. And here is the scatter plot, and it's not really the greatest looking data for running just a simple regression. It actually looks like there may be a little bit of a bend there, but at any rate, just to kind of show you what these look like, I'm going to click on add fit line at total, and you can see there's the regression line. Well, actually it looks fairly straight, but there is kind of an outlier right here, it looks like, but nevertheless, this is kind of the general relationship. And so this equation here, the 2.24 plus 0.37 times x, that is the equation. And so the 2.24 that we saw in our table for mastery, the regression of achievement onto mastery, that was the intercept or the constant. The 0.37 is the slope. So, and then the 0.255 that you see right here is the R-square value. So kind of going up here and looking, there's the 0.373 basically, the intercept being 0.242, which again, there it is. So it's rounded off a little bit. Let's look at it in relation to the interest variable. So I'm going to move that over. click on OK. And so now this is what the data looks like. And so I'm going to double click on here, click on Add Fit Line at Total. And so that's the line of best fit that's being fitted to the data. And so this is a prediction line. And essentially what we have right here, we have the intercept and the slope. So it's a little hard to read, but it's 1.99 plus 0.38 times x. So that's the regression equation. That's the prediction equation. And so you can see that there seems to be a positive predictive relationship in the data. So now we're going to go to anxiety and add that and take a look at it. And so now when we double click on this and click Add Fit Line at Total, this is the model that we generated in the last regression. And so you can see right here the fit line kind of going in a negative direction. So basically, as scores are kind of increasing on anxiety, we have lower scores on achieve. If we have lower scores on anxiety, then we have essentially higher scores on achieve. So that's a negative relationship. And there you go. So now let's look at this with a multiple regression. So I'm going to go to regression linear, and instead of using each of those variables individually, we're going to use the complete set. And I'll click on statistics and other things that I will ask for. I'm going to ask for part and partial correlations. And oftentimes we'll ask for collinearity diagnostics as well. I'm not going to get into the issue of collinearity in this particular video or looking at assumptions related to the model, but these are handy oftentimes when you're analyzing your data, and I'll address that in another video. So I'm going to click on OK, and so now you can see that the model R-square is 0.362, and like I said, basically what's happening is that in this particular case, this is the model R-square. So R-square of let's see what that was. I think it was 0.362. Yeah, 0.362. That is the R-square, and that's reflecting the combined influence, if you will, of the set of predictors on the independent variables. So, on the dependent variables. So, as a set, mastery, anxiety, and interest are accounting for 0.3 or 36.2% of the variation in the achieve variable. So as a set, they're accounting for a pretty good chunk of the variation. So the F-test is a test of the combined set of predictors in accounting for variation in our outcome variable. So you can see right here the F-test is indicating statistical significance. So we would infer that the population R-square is significantly greater than 0. That's like I said, that's a pretty good percentage of the variation that is being accounted for within our sample. The multiple R is essentially the correlation between the set of predictors or set of independent variables and the dependent variable. As I said before, it's going to range between 0 and 1, and basically we would interpret the correlation in terms of magnitude only. So we're not going to be talking about a direction in terms of a correlational relationship, because this value can never be a negative value. It will always be positive, and it will range between 0 and 1. So the correlation between the set of predictors and our outcome variable in this case is 0.602. And like I said, this is called the multiple correlation, and the R-square value is unsurprisingly the square of the multiple correlation, and the R-square value is referred to as the coefficient of determination. If you want to know a little bit more about that conceptually, basically what's happening is we're taking the information from the set of our predictors, our independent variables, and we're essentially generating a predicted value on y, or a latent variable that is incorporating the information from our measured variables here. So essentially we're generating predicted scores on y, which is sort of a latent variable, incorporating this information from our our independent measures, and then the R square and the multiple R are essentially reflecting the relationship between, so there's our multiple R and our R squares, reflecting the relationship between this sort of composite of the information from our independent measures and our actual dependent measure. So that's essentially what's going on in this case. So that's what the R and the R square is essentially capturing. So at this point, we've demonstrated that there is an overall relationship between our independent variables and our dependent variable. But then we want to go back and we want to look at the individual contributions in the model of our independent measures. So I'm going to go down to the coefficients table right here, and you can see that we have our mastery, interest, and anxiety variables. So the thing is that just because R square, our R square coefficient, we would infer that the population R square is greater than 0. That doesn't mean that all of our independent variables are contributing in the same fashion. And in fact, it can be that we can have one or more of the independent variables that are not significant in the model. So that's completely possible. So we want to test out which of our variables is really which of our variables are contributing to the overall association between the predicted scores on Y and our actual scores on Y. And so we essentially are going to test each of these regression coefficients for statistical significance. And we're pretty much following the same logic as before when we were talking about the simple regression. The big difference in this case is that the regression coefficients that we have right here reflect an adjustment for the fact that our independent variables exhibit correlations amongst themselves. So these are, in the context of a multiple regression, these coefficients for within our model, these are essentially referred to as partial regression coefficients. So in the simple regression context, we were just referring to them as just the regression coefficient. In the context of a multiple regression, we're essentially referring to partial regression coefficients. So, and basically our hypotheses concerning each of these, we're going to be carrying out t-tests for each of those regression coefficients, but there's going to be a separate hypothesis for each of those. So so you can kind of mix and match even. You could have all of our by the way, all of our null hypotheses are that the given regression coefficient, and I'm just going to denote that as beta with a little subscript for k, reflecting a given regression coefficient. So all the null hypotheses would be that the regression coefficient for a given predictor is equal to 0. And then when it comes to the alternative hypotheses, we would have one for each of those. So basically the population regression coefficient for a given independent variable, we can have a non-directional hypothesis, meaning that the regression coefficient is not equal to 0, or we could say that a given regression coefficient is going to be greater than 0 or less than 0. So just keep in mind that this right here, this would be a case of a non-directional hypothesis. And with a non-directional hypothesis, you're using a two-tailed test. These are directional hypotheses, in which case we would be using a one-tailed test. So for this demonstration, I'm mainly going to focus in on just using a non-directional hypothesis, with the caveat that I could have easily come up with a theoretical argument for these two being positive predictors and this one being a negative predictor, which would entail a directional hypothesis for each of those. So at any rate, we can see that mastery is the unstandardized regression coefficient is 0.214. and it would be treated or deemed as statistically significant. So the unstandardized regression coefficient, we would interpret this to mean that for every one raw score unit increase on mastery, there's a predicted increase of 0.214 raw score units on the achieved variable while controlling for the other predictors. So keep in mind, we're controlling for the other predictors, which are correlated with mastery. Interest, there is a positive predictive relationship, and it is statistically significant. So we would say that for every one raw score unit increase on interest, there's a predicted increase of 0.261 raw score units on achieve, controlling for mastery and anxiety. And then anxiety, there's a negative regression coefficient, and we would say that for every one raw score unit increase on anxiety, there's a predicted decrease of 0.07 raw score units on achieve, controlling for the other predictors. But you can see that anxiety was not statistically significant in the model. So when it comes to making a statement about the overall R-square value, the variance accounted for in the dependent measure, it looks to be due largely to mastery and interest as opposed to anxiety. So anxiety does not appear to be contributing uniquely to the variance that's accounted for in our dependent variable. So then looking at the standardized regression coefficients, these are most useful in the context of multiple regression. In simple regression, the standardized regression coefficient essentially reduces to the Pearson's correlation between a given independent variable and the dependent variable. In the context of multiple regression, these coefficients reflect the relationship between between standardized versions of mastery and achieve, or interest and achieve, while controlling for the other independent variables. And so the nice thing about standardized coefficients is that it helps you to sort of assign a rank ordering of the relative contributions of the independent variables when it comes to accounting for variation in the dependent variable. The unstandardized coefficients are essentially scale dependent. What that means is that the size of these coefficients, we can't rank order the independent variables in terms of their relative contributions based on the unstandardized coefficients, because these variables all have different standard deviations. So in other words, the scale of measurement for each of these variables are different. And so by virtue of that, the coefficients in terms of their relative, reflecting the relative contributions, it's really kind of impossible to detect that. So to make a judgment about relative contributions of the independent variables and the size of those relative contributions, we can use the standardized coefficients, because it's reflecting the relationship between a given independent variable and the dependent variable, assuming that the independent variable and the dependent variable are in z-score units. So, so all the coefficients right here are assuming that our independent variables are in z-score units. So they all have the same scale of measurement. So that allows us then to sort of rank order them and then judge kind of the relative magnitudes. So you can see right here that mastery, interest, and anxiety, you can see that anxiety right here has the largest absolute value. So we would say in this case too that interpreting the beta coefficient, for every one z-score unit increase on interest, there's a predicted 0.36 z-score unit increase on achieve, controlling for the other independent variables in the model. The second largest coefficient is for mastery, so we would interpret this coefficient to mean that for every one z-score unit increase on mastery, there's a predicted increase of 0.29 z-score units on achieve, controlling for the other predictors. And then the weakest predictor is anxiety, and it's the coefficient is negative 0.091. And we would say that for every one z-score unit increase on anxiety, there's a predicted decrease of 0.09 z-score units on achieve, controlling for the other independent variables within the model. Okay, so I think think at this point, oh, one other thing that I do want to draw your attention to, since we're already here, you'll notice that in the model summary for our regression analyses that we have, again, we have the R-square value, and that this is essentially the again, the proportion of variation in the dependent variable accounted for by the independent variables within our model. This is, again, being used as an estimator of rho square within the population. So essentially, I'm just going to denote this as rho with a rho square with a subscript of y dot x, x1 through 3 in this particular demonstration. And the thing about it is that this estimate, if we have larger numbers of predictors and smaller sample size, that relationship, essentially what can happen is it can lead to a bias in the R-square value. And so in other words, in this case, it would be a positive bias, meaning that we would potentially overestimate rho square, or the population R square. And so the adjusted R square is essentially a computational solution to that problem. Essentially adjusts the estimate of the R square value downward based on the number of predictors and your sample size. So in this particular case, you can see that the R square and adjusted R square are not all that different. However, in some cases, it can be dramatically different, and you want to make sure that you do report on the adjusted R square as well, particularly in those cases where there is a considerable difference. The difference between R square and adjusted R square, that's referred to as shrinkage, and basically, like I said, it essentially reflects the idea that we have a positive bias in the R square value, and so we want to adjust for that. The F test proper is a test of the R square value, so it's not a test of adjusted R square. So when you're reporting your results, you'll report the R square, the significance test, and then you can report the adjusted R square in addition. So that pretty well concludes this discussion on kind of discussing aspects of simple and multiple regression. It's kind of a long video, but I wanted to make sure that we covered covered a lot of our bases with respect to running the analyses in SPSS and looking at our data in different ways. And I really wanted to again highlight the reason why if we have separate independent variables that we want to consider as predictors of a dependent variable, why really multiple regression is oftentimes preferable to running separate simple regressions. So that concludes this discussion, and I hope you find this video useful.